Hey, thank you. Thank you for inviting me and for listening. I guess I want to tell you about something about in learning in some strategic queuing systems. I guess with this seminar, I don't have to start with a lot of introduction of why we care about price of energy or games or here you go. Price of energy or games about, in general in games. But generally, I'm going to still consider, kind of outcomes and how good the outcomes are. And as the title suggests, I want to focus on learning outcomes rather than Nash Equilibrium, assuming that people are learning. And I'm going to maybe not spend any time on sort of arguing that learning is maybe a more reasonable outcome in a repeat or more expected outcome in a repeated game than Nash Equilibrium. I guess I forgot to say in the beginning that feel free to interrupt. In fact, if there are any questions that you might have, I suspect other people would appreciate the answer to those questions too. So it's better if you ask. And I'm doing my best to monitor the chat window, but that's always a bit challenging. So if you could interrupt, that probably is an easier way to get your question answered than putting it in the chat window. Okay, so I said I'm going to skip through this. I'm going to propose that we think about learning outcome, but one of the messages of the talk I want to tell you is that it's unclear what we should mean by learning, and that the classical thing we used to mean might not work in a lot of different settings, or might not work well enough in a lot of different settings. So what's the classical learning that we somehow grown to love as satisfying all kinds of conditions is no regret or HANA consistent. And no regret and HANA consistent is nice in two different ways. I guess one, so that's the condition. It says that if action T, the action vector T is what the players did at time T, and I take the person I who is participating in it, take his cost over the time, he should not do any worse than any single action with hindsight. With a little bit of error, which I guess we call regret. And what's nice thing about it that this is very reachable. There are a million different algorithms million simple, elegant algorithms that achieve this consistency. That's one nice thing. And the second nice thing, which we grow to love, is that the price of energy work extends. So price of energy was meant to be the worst case over Nash equilibria of the possible outcomes, of the social welfare of the possible outcomes. And if you turns out that almost all the proofs we have for price of energy extend to if instead of price of energy, we assume that the players are learning. And I guess, as you can accidentally see here, I mixed costs and utility, and maybe I will continue doing this throughout this talk. A second ago, price of energy was expressed as costs, and here, regret was expressed as cost, and here is expressed as utility. Hopefully, it's not too confusing. What I want to start with this talk is attack the second part here, namely, the key phrase here that I want to wonder about is the stable game. So the assumption on these extensions, which hopefully most of you, all of you have seen is that every time we repeat, so if I go back to this slide, there are many copies of this game. Every time we repeat the game, we're playing the same game and a fresh new copy of the same game. That is no carryover, no leftover effect. There is nothing between the games, well, except for, of course, people carry their learning. So the only thing that happens between the games is learning, and I'm going to claim that that's actually not reasonable in almost all games or very many repeated games. And I want to challenge you to think about, other games where this is an issue and see whether we can prove similar interesting theorems or think about the right learning ways for other games. I'm going to focus on the queuing system that I promised in the title. So why do I think it's not reasonable? I guess the comparison is nice to think about is traffic. And I guess it depends what is my time scale. So if I think of my traffic game modeling the morning rush hour, then I guess it's reasonable. No matter how bad my Monday morning was, even in Israel, where I gather traffic can be really bad, by Tuesday morning, the cars are gone. Hopefully overnight, the road's cleared and there's no traffic jam there. But if I think about the either car or packet traffic on a different scale, like on a minute by minute or even 10 minutes by 10 minutes kind of scale, then it's not true. If there was a traffic jam on the highway to Tel Aviv 10 minutes ago, these guys are still there. The traffic jam is just as bad as it was 10 minutes ago, or maybe a little bit different. In the packet context, packets, when there's a jam in the routers, then the routers drop the packets, and then those packets will need to get resent in the next run. So the very same packets are causing the traffic jam. So what I'm going to ask is, what can we say in price of energy in repeated games in stateful systems, that there is an actual game dependence, that is the state of the game evolves depending on what's happening in the previous round. What can we say about learning and what might be the right learning? So I'm going to ask the style of question that I generally like better than the price of energy. How much extra capacity do we need to ensure good performance? So this is, I guess, sort of a dual question to the price of energy. I'm not asking how much worse the performance gets, but rather how much extra should I give them to guarantee good performance? And I guess the question I was more thinking that is very open-ended is what's the right way to learn? Is no regret learning reasonable? And if not, then what might be the right way to learn? So that's the sort of high-level goal. The actual model I want to tell you is that
Eva,
yeah.
if I may,
sure.
At least the game theoretic dynamics that yield Hanan consistency. For example, the very simple one, for example, which I know for sure, which is play proportional to the regret, they work for any sequence of games so long as the payoffs are uniformly bounded. That's the only restriction that is needed. I don't care which game every day it is played. Could be a completely different game. Now, I'm not sure that that's entirely true about some of the computer science dynamics that have various other tricks in them. But as I said, in game theory, we are used to this variable game, and we don't care.
I think you should care. You will care. No,
I will care if it's a stochastic game where, in fact, the game today influences in a very specific, well-known or partially known way the game tomorrow. That's a different story. Then we talk about dynamics in stochastic games. But okay, I'll let you.
So what I mean by carryover effect is exactly what you said. The second one, the game today, or the outcome of the game today influences what happens tomorrow because it's a concrete game in a specific way. And I do agree that no regret learning works, and even we'll show you, price of energy style theorems that if everyone does low regret learning, then reasonable things happen, it still will suggest that there might be a better thing to do here, because your actions have an impact for tomorrow, which no regret learning, any of these classical algorithms do not think about. So
Okay, good. So,
I do agree they
should...
work. I do agree they work, but I hope I will convince you here that there might be better things you might want to do.
No, I agree with everything you said. So we should better think of the setup as being a stochastic game. That's probably
Yes,
the better,
well, tell
model
you
in mind.
in one tiny second, one particular stochastic game, which I'm going to think about as my sample game. So
Okay.
here is the game I'm thinking about. It's a super simple, oversimplified version of a queuing game. So there are a bunch of queues. Each of them gets packets at the Bernoulli process at some rate lambda I. So it's a discrete step game. Every discrete step, the QI gets a new packet with probability lambda I. And it would like to get it to one of the servers and get it served. Maybe just for making both my life complicated and actually one of the induction proofs simpler, I allow the servers to have a probability of being successfully, of serving something successfully. That's a probability in UJ, depends on the server. And what makes the game, or what makes it competitive, that each step, each queue can send one packet to one of the servers. And then I guess, as you see, maybe two queues sent to the same server, then this compete for the service. And I'm going to assume that, every server can only process one packet at a time, and that the particular packet gets served is maybe these packets have timestamps and it's serving the oldest packet and sends the other one back. So this makes it a game between these queues who, send their packets to the servers, and sometimes it gets served and sometimes it gets sent back to them. And I guess their goal is to get served, which means two different things. First of all, they prefer better quality servers, if at all possible, but they also prefer servers that the other queues are, certainly the other queues with older packets, don't send to, so they can get served. So in some ways just a discovery of which one is the good server, but also a game between them so that they ideally, get out of each other's ways.
Eva?
Yeah.
So the assumption here is that any queue can send to any server?
Yes, so that's a simplifying assumption, which probably I should work to get rid of. At the moment, every queue can send to any server. So it's a complete gap between them. And second, for those of you who are queuing theory background, another way life is super simplified. These are, I guess, internet packets or somehow very identical packets, not the classical queuing theory version. That is, every packet's identical and the serving time everywhere is identical. The server's ability to serve them is all identical. Everything is very symmetric, other than the rates at which packets arrive, or possibly the rate at which servers can serve these packets, that might not be identical.
So, Eva, can the queue send it to multiple servers or
no, they choose one packet. So that's the server can send at most one packet of one of his unserved packets, and oh, sorry, that line here. Each queue can at most one packet to one of the servers.
Thanks.
Eva?
Yeah.
Can you please repeat the assumption you make about the priority of the servers? So they attempt to serve oldest packet, but you also added another assumption.
No, I did not.
You did not.
I mean, they have a MuJ probability of being successful at all, and if there are multiple packets showing up, then they try to serve the oldest one and send everything else back. So that's the model. Now, before I can tell you, so and I'm going to think about what's a Nash equilibrium of that game, or what might be a Nash equilibrium of this game. How should the servers behave in a Nash equilibrium? What happens if I have them learn in a Hanan consistent way? And again, what I promise, that's the question I'm going to ask is, how much server capacity do I need to make sure that the queues will clear? So what does it mean to clear? It means that, well, how do I measure the quality of this system? I mean, ideally, here is something that's definitely horrible quality. If one of these queues is getting stuck with an infinite queue of packets behind him, and it's built up growing and growing over time, then the system isn't stable. It's like, some queues get some packets get never served here. If instead I can keep the queues bounded in expectation, the queues of the packets bounded in expectation, then I claim that the system is performing reasonably well. Rahul is asking me what's the utility of each queue, which is a good point, and I'm just sort of assuming the natural utility. They just want to get their packet served. So they're trying to learn what is the place, what is the server where when they send the packet there, they tend to get it served, or they can get it served as fast as possible.
So in a way, a total waiting time could be a good utility if you want something
Total waiting
specific.
time, yes. Yeah, total waiting time is perfect. Throughput and other equally good. These are effectively equivalent. Not quite, but maybe total waiting time is a better that Sergio suggested. Though throughput is great also. Okay. So before I can talk about, how much extra capacity do I have to give the system when they're selfish, I need to ask myself the question of, what's the baseline measure? Suppose I coordinate them, tell them what to do, how much capacity do I need? And I guess this is not so hard to show, and hopefully you guys all will believe me. So in order to figure out the capacity, it's better to make some simple normalizing assumptions, like here is one. The queues are ordered, that is the first queue has the highest arrival rate, and so on down. And the servers are similarly ordered, where the best servers are on top. This is just a notational trick. And I claim that the condition for a centralized system to be able to serve all the packets or keep the queues bounded is this. That is that if I take the top queue, the single top queue, so that would be the k equals 1 special case of this condition, take the one queue, there should be a server with service rate higher than the rate of this one queue. That's not too surprising. Remember, the queue can only send to one server at a time. And if the service rate on the best server is not good enough, then he's host. Like, he's getting new packets at probability lambda 1, and there is no server that can serve it at that rate. There's nothing much he can do. Similarly, the top two queues, which can send to 2 servers if they coordinate, ideally, they maybe will use the top 2 servers, should have a total service rate of at least as much as the sum of the arrival rates, and so on for every case. So the top k queues, or the highest arrival rate k queues, should have total arrival rate strictly less than the total service rate of the best k servers. And this is all because they can only send to 1 packet in each run. So k queues can only use k servers. And so we see that the top k servers need enough capacity. And once you give them this much capacity, a bit of sort of bipartite matching style coordination between them and the classical queuing theorems for 1 queue, 1 server will show to you that the queues will remain bounded. The size of the band, of course, will depend on the size of the gap in the strict inequality. hopefully this is very believable because I wasn't planning to actually go through any proof. But hopefully the necessary part is maybe even more obvious, and then the sufficiency I hope is very believable. Here is the two theorems I want to tell you about. So here is theorem 1. It's all joint work with my student Jason Gaitonde. If every Q uses a no regret algorithm, and I don't that much care which one, but as long as they satisfy the Hanan consistency condition, and I gave twice as much capacity to the servers as was necessary in the centralized version, so a factor of 2 up in capacity, then the Q lengths will not grow linearly. That is, we will not have a linear buildup of packets after any Q. They'll succeed.
So
this
suppose
is
just one
the answer to Sergio's question. I'll let you answer in a second. Is that no regret is not so bad. We get something quite reasonable here. That is, if I give them twice as much capacity and they're doing a no regret learning algorithm, then they did actually succeed in getting their packet through. Yes.
Suppose there's just one server whose mu is bigger than the sum of the lambda i's. You still get this factor of 2? No. I'm trying to understand if the factor of 2 comes from the fact that there are multiple servers or just from the system itself.
Multiple servers. If there is one server only, there is really no game. It's just a classical queuing system with a priority, or almost classical queuing system with a priority, because there is not, they don't have a strategy. There's only one place they can send it. So
no, but there is still but there is still the coordination. Oh, I see. But because you have the tie-breaking rule that he always serves in a certain order, so it doesn't matter who sends, he's always going to take the oldest. I see. Yeah. Okay. So with that thing, then there is no game already. Okay.
Actually, in that case, if I have enough capacity, it doesn't even matter that I have a tie-breaking rule. Like if there's only one server, they always send to that server. The server has enough capacity for the sum of the lambdas. One way or another, it will, like in some order, it will serve everything. The total arrival rate, which is the sum of the lambdas, is less than the capacity. And they're not wasting any, they never make mistakes in wasting capacity.
Yeah, I see. Okay, so that
if there are multiple servers,
that's
the coordination might waste capacity. How do they waste capacity? You and I compete for the same server, where I left the other one on empty. That was wasted, and it's hard to avoid the waste if you don't coordinate. But with a single server, there's nothing to coordinate on.
Okay, very good. Okay, that clarifies it. Good.
Okay. Eva, I have another question. Is this result related somehow to your result of selfish routing, where you need twice as fast roads?
Don't know. It's magically the same number, right? Though 2 is a very simple number, so it occurs in a lot of things. I'm not aware of any connection, but I did notice it has the same number in it. Maybe not.
Thanks.
So here is the version.
Eva, can I also ask a question?
Yes, definitely.
So related to your discussion with Sergio, so here you double the bandwidth, but you could instead double the number of servers, and exactly because that coordination is the problem, then that might also help, right? I mean, this formula, right?
Might also help.
Might help more, I guess. Exactly because of the coordination problem.
Yeah, I guess we have to be careful what you mean, because very many bad servers are not helping. But if you double it in a sense that you give me a second copy of every server. So for every server lambda, I have a second copy with exact same lambda, then yes, that helps. So that also is fine.
I think so. I guess my question was, do you know if this would help more, I guess, than like just doubling the capacity of each of the n servers, or like having 2 n servers?
That's a good question, actually. The way our theorem is stated, it's not even covering that case, but excellent question.
I think because if you had more servers, it seems that the coordination problem may be even more severe. So maybe it will help less.
Yeah, it could be. These are all, that's a great question of what it does. The funny part is that this condition,
but they should somehow learn to like distribute themselves better.
Right, this condition will be satisfied on not on like the even numbered case, it's okay. The odd numbered case, it may not, which is a weird. I need to think about Sigal's question. This theorem does not prove that it helps, but intuitively, I think she's right, because we're adding, or I hope she's right, because we're adding sort of big capacity servers, and that should be helpful.
Cool.
That's a nice question. I need to think about whether it works or not.
Okay, another question, just as a benchmark to understand. Suppose that the queues are sending it, suppose it's a randomly assigned. Each queue randomly sends. What's the right number instead of 0.5?
That.
Sorry?
The next slide, which I just showed.
No, that's patient. I said that random.
Random. That's the.
Which means that it's completely. They don't use. They are not smart at all. They just there's a random sending of. So to understand what no-regret does at all.
I did actually answer your question at least. So when I say the patient, that will turn out to be an equilibrium result, not a learning result. But the worst case for this equilibrium is identical queues, identical servers, and the people sending randomly. You will not be too surprised to learn that that's a Nash equilibrium, uniform randomly. That's a Nash equilibrium, because everything is so damn symmetric. It's hard to avoid the uniform random behavior to be a Nash equilibrium, and in fact it is. And as you know, when these numbers get big enough, then the limit of how much capacity you are wasting is 1 over E. So the extra capacity I should give you is E minus 1 over E fraction. Like it's a boss and bins question. If I'm asking not how much you need, but rather how much capacity am I wasting if everyone behaves randomly, then in n boss and n bins, a 1 over E fraction of the bins gets nothing. That's the wasted capacity, and I have to give you enough extra capacity to compensate for that. I'll show you the example in 10 seconds.
But I don't think, unless I'm mistaken, the number should be less than 0.5, not higher than 0.5. It's 8, because I'm talking about guaranteeing no matter what the structure of the problem is, not in the IID situation. Yes?
Oh, I see.
So, so you just have an arbitrary set of lambdas and mu's, and the behavior is completely random. Then what is the, instead of 0.5, what is the number there? Can it be arbitrarily small, for example, or still, I don't know.
I think it's arbitrarily bad. Like if
because
if
that
really
says
bad,
that no-regret does something. Okay, I mean, but if that number says 0.25, I'm just saying I have no clue what it is. Then no-regret is a little better than random, but not much more.
Sorry, Sergio. I was thinking that that you're asking in a sort of situation, very symmetric situation, where this uniform random behavior is reasonable. If mu's can be arbitrarily, you might be stupid enough to send your packet, even if you're just alone, there's no game here, a single player, and dumbly enough, you're sending randomly, life will be really bad.
I don't know. There may be only 1 over n. I don't know. I'm not sure. I'm not sure, because giving random means even if once I send it badly, maybe multiplying by a factor of n or k or something.
Yes, that's what I mean.
You'll overcome it. The question is whether it's something which is bounded away from 0 or not. I don't know. Just as I said, it's a benchmark from below. That's all.
Okay, it's definitely at best 1 over n, where n is the number of servers. I don't know if that's good enough, but I view that as horrible enough. It's not a constant. It grows with the number of servers, whereas that number did not.
So Eva, did you just mention the case where all the mui's are the same?
That's the worst case for the second
So
theorem.
that's the worst case. So I think regarding Sigal's question, we can think about the extreme where you don't double the number of servers, but maybe you can take a huge number of servers and just divide it into very small capacity servers. And that would be maybe.
So that's not helpful, right? Because people can send to one server at a time. So a big capacity server is better than 2 of the half capacities.
Okay.
Less coordination needed and same total service capacity. Okay, the message I want to get to, and I should be careful not to lose sight of that I definitely want to get there, is that something is wrong with no regret because it's not sufficiently patient. Unfortunately, our patient result is only in the blue slide here, only at Nash Equilibrium, and there we need a bit less extra capacity. It's not horribly less, but a bit less, not a factor of 2, but only a factor of, I don't know, 1.6 something to invert this. So in my optimistic way, which I'm going to maybe give up on, I wanted to show you a little bit of sites of proofs for both of these theorems. I'm definitely going to try to cut the first part short because I want to get to the sort of interesting question here of what way is this number, why is this number better and what's wrong with no regret learning? So, but you know, I still have a couple slides here of the idea of the why is no regret learning any good at all? That's a potential function proof. The potential function I'm using is basically a funny function of the sum of the ages of all the packets, or maybe a better way to view it, if phi tau is the number of packets tau old or older in the system and summed over all all taus.
So it's a total age. It's the sum of the ages.
This is the same as the sum of ages. The main theorem we're using is a beautiful probability series theorem of Pimentel and Rosenthal, which says that if a random process is sufficiently regular and has negative drift whenever it's large, then it remains bounded in expectation over time. And the main thing we want to prove that no regret and the factor of 2 slack will imply a negative drift in this function phi when the queues have large backups. So when phi is large, so that means there's some really old packet in the system or sufficient number of packets in the system, then I expect that this function, this square root of phi, will decrease.
But why 2? Why 2? Why do you need 2? That doesn't explain it.
It does not yet, but it will in a second. So, okay, so why does no regret help? Which is, I guess, what, and why do we need a factor of 2? So what I'm going to do is look at sufficiently old packets, so all the packets that are tau old or older, and notice that given my priority scheme, they have priority. So wherever they send, even if they compete with each other, one of them will get across, or get a chance to get served. So look at a reasonably long window at the best and fastest servers, and I claim that there are 2 cases. Case number 1, that these queues that have very old servers, either throughout this window, quite a lot of times send to these very best servers. And if that happens, then they should get served at this mu-r, a sufficiently high rate, higher than the arrival rate, and therefore the sizes of queues should decrease because, again, the old queues are doing a good job sending to the sufficiently high quality servers. this is the good case and has nothing to do with no regret. No regret will come in the second point. Suppose they don't. They make a mistake and send it to the wrong place. That's when I'm going to use the no regret condition. And this is what the no regret condition will say is this guy sending to the wrong servers. But remember, at the right servers, they should have had they would have had priority. They just didn't send there. And because they have priority, and they're not sending there, not other road servers are not sending there either, no regret will kick in. They should regret not doing this. So due to the no regret condition, the packets either have regret or they manage to get served at a fast enough rate there too. And then I'm going to not focus on a single age, but do this simultaneously in all the ages. So just to get back to Sergio's question of why did I need a factor of 2, I guess this is the style of argument that usually needs a factor of 2 without having emphasized it, but let me try to say it at least in words. The two cases I'm separating is either you use the servers a lot, say at least half the time, or if it's half the time empty, then that emptiness or empty of these old packets, then its emptiness generates regret. And that style argument has a trade-off at the half. Like either it's half used or it's half empty. If it's half used, I'm golden, it's half used. If it's half empty, you should have regret about this. And that needs a factor of 2. And in fact, this factor of 2 is tight. To be honest, there's a bit of technical details here, which I definitely will sweep under the rug. Because this is an infinite process, every bad thing will happen every now and then. So I will need, I guess we need a better learning algorithm that the no regret conditions should hold with high probability. And what I really will sweep under the rug that the Pimentel-Rosenthal theorem as another condition, which I wrote there as sufficiently regular, by which they mean it has bounded moments. And at the moment, the one I declared, this guy here, doesn't actually have bounded moment. In particular, when I clear a packet, this phi function goes down by the age of that packet. And even root phi can go down by root of this, which is not bounded at all. To make it bounded, I need to switch rather than using this potential function. I should do deferred decisions, focus on the ages of packet, and take the expectation of this number rather than the actual number, which is a technical detail I'm going to sweep under the rug here. Again, all that happened is intuition was that potential function, but to make it regular, I have to do deferred decision and focusing for every queue only on its oldest packet and not on all the packets in the system.
Yeah. So a question about the theorem. So the theorem doesn't say that the queue length grows sublinearly with high probability, but it seems impossible to have a probability one thing, right? Because if you're not lucky and the generation of these
yeah, indeed. It's all it says that the queue length remains bounded in expectation throughout the time, but not with high probability, in expectation.
In expectation. Okay, thanks.
And you're right. There is you can have a sequence of bad events here where arrival is insanely dense for whatever reason. It has a small probability, small but positive probability, and there's not much you can do about it. There's just not enough capacity in the system to clear it.
Thanks.
This factor of bound 2 is tight here, which maybe Sergio will already believe me from the style of the proof, but we actually have a matching example that indeed it is necessary. Again, I slipped or ran through this a bit faster because I want to get to the sort of interesting part for me, for open, of what exactly is the right form of learning. And to do that, I want to first give you an example, and maybe that's the main thing I'm going to give you, the example of what's wrong with learning, or what's wrong with no regret, actually, nothing with learning, what's wrong with no regret. So here is a very simple example. There are two queues, each of them have a little bit above 50% arrival rate. So roughly speaking, getting packets a bit more frequently than every second step. And we have two servers. One is really perfect, or serves all the time, and the other one is worse than 50%. And first thing I want to claim that if you want a no regret outcome here, you can only do one thing: send all your packets to the top server. Now I claim this clearly has no regret. You know, these two queues are very symmetric. So when they both send to the same server, they're going to just split the service rate half-half. So they're getting a 50% service rate. And remember that mu2 is now below 50%, so they have no regret. They're getting served half the time here. If they come down here, it's less than half the time. So this is the no regret outcome. This is the only no regret outcome. Of course, it's also equally obvious that this is not good enough. The total arrival rate is above 1 and the service rate is 1. So clearly there's linear growth here. And if they were to deviate, they're going to get regret. That is, if they decide that, you know, every now and then I try this other server, then they're going to learn that the service rate is only 47% and the service rate here is better, so they have regret. However, moving to this inferior server, say with the little bit of probability I suggested here, actually helps. And what I mean is helps even if you're selfish. So the first thing to note is that, of course, it looks like an altruistic move. When 10% of the time you came down here, that will help the other guy because 10% of the time he's alone and he can get served. But because of the time priority, it will help you. So because you helped him, his timestamps typically will be more modern or less old than yours. So whenever you go up there, you tend to have the older packet. So your service rate here will go up to above 50%. In fact, quite a bit above 50%. So in some way, your regret feeling for the 47% will, but even worse, your service rate there is best. But yet, if you do this, both of you get fully served. So you lost a little bit in service rate here, 47% only. And in fact, your ages got worse. But overall, actually, both of you clear, and it will become perfect. So if I take the particular version of the objective function that one of you suggested, and I have to go back on the chat window to remember who it was. Sorry, not that head.
But Eva,
I guess Rahul suggested throughput. Someone suggested maybe in words, maybe that was Sergio, that speed at which you get served. The top queue is better than the bottom one in this system, but both of you clear all your packets. Whereas if you believe in no regret, then neither of you will clear all of your packets. You both have an infinite lineup in packets after yourself. Yeah.
What if the first one also starts doing that? So his packets are not going to be old, are not going to be younger than the second guy.
So even
because
that
he's losing because the second guy now has his packets are usually a little older, right? Or in equilibrium, they are the same.
Fine. It's fine that way too. If they both do this symmetrically, then the way they both gaining is that on the top one, they're alone 10% of the time, and that helps. So they still have a better service rate up there. This time he has a better service rate because he's older. If they both were doing this, then he also would have a better service rate. And this time, because there is a positive chance, as in 10%, that he's alone. And that's helpful.
So in fact, the 0.9 and 0.1 are chosen in such a way that the rate at which the two Qs go down is equalized. Is that correct? Because they both are 0.51 arrival, which means that the way that they same arrival rate, which means that the serving rate of both Qs essentially, the actual serving rate is equalized. They are both the same length, right?
Yeah. Yes.
And that's how the 0.9 and 0.1 are chosen, or whatever.
I didn't choose the right numbers. I only chose roughly
I mean,
the
there are
right
some
numbers.
right numbers there.
If I were to take the equilibrium of this, then yes. So here is what we're trying to. Oh, I lost the cursor. Here's what we're trying to do. So that first of all, what's wrong with no regret, and maybe you guys will see it already, but I want to drive it home. If I think of what no regret algorithms do, and this time I'm not actually thinking of the classical Hannan algorithm, but maybe the modern ones that I call simple and elegant in the beginning of the talk, they do explore, exploit. What they do is every now and then try this possible X, and if it's doing very well, then they switch to it. And actually the one that Sergio suggested, that they behave proportional to the regret, is the same idea. Try X every now and then, and if they decide that's working much better, then they should switch to it. If I remember that this is a stateful system, I should improve my notation to the following. The cost at time I time t doesn't only depend on what you did at time t, it depends on the whole history. So this is maybe a better notation for this. And then what these algorithms achieve is this not so good looking condition. You do better than you would have done with X if you did the explore every now and then with X without changing the history. But what I really would want to do is I want to think about the long-term benefit, which is what we call patience. And possibly I want something like this. How much better you would be if you consistently did that X thing, or at least did it for quite a while rather than for one tiny second. So explore, exploit, which is the philosophy under which these no regret algorithms operate, trying things and sticking with the one that's good, it's really not good in a system where in order to see the benefit of your action, you might have to do it for a while. Like you have to have patience in testing this action. Oops, I lost it again. So again, the theorem we have is not about learning, and that will be the open problem. And if there is a good learning algorithm that achieves this, the theorem that I will tell you a little bit about is an equilibrium statement with an equilibrium analysis as the proof. So every QI picks a fixed randomization over servers, and that generates a Markov chain of these Q ages. And we look at, maybe here I'm more precise, is giving every Q objective function of minimizing the expected asymptotic aging rate of its Q. So look at the age of QI at time t divided by t, and you want to drive this limb soup to as low as possible, hopefully 0. And you're running a Markov chain with this randomization, and I ask what's the Nash equilibrium of this game. So just to get you some taste of what kind of thing might be going on here, here is a very simple Nash equilibrium example with a symmetric example that I worked out the Nash equilibrium for, and maybe this is a more interesting Nash equilibrium than the completely symmetric one. I guess the two side servers always send, so side Q sent to the top side server, And these two guys are randomized with these particular percentages. And this time I did work it out. This is the Nash equilibrium. And all Q's will clear if the arrival rate is less than 0.73. Remember, the optimum would allow them to go up to 0.75. So they're not losing so much in this particular example. There's a lot of different questions you can ask here. You know, you can even start with what if you have a randomization, what are these asymptotic aging rates? Is there even exist an deterministic equilibrium here? And what's the price of energy? I guess I want to certainly tell you what the worst case is. So here is something that hopefully you believe is an equilibrium, n identical servers and n identical queues, and they all serving uniformly at random. And this is where my E over E minus 1 band is coming from. You know, this totally symmetric behavior, not too surprisingly, is a Nash equilibrium, and 1 over E fraction of the servers is getting wasted. So I need to give them that much extra capacity to succeed. It is a bit harder to argue, to do the equilibrium analysis that this is the equilibrium. Maybe one of the difficulties is that in many cases, including the example above, there will be very many equilibrium, very many tight sets. Okay. To get you some taste of what we're doing, first of all, working out how the queues will age, that's not very difficult, and it's a complete copy of what happens in a single queue and single server. So if you have a single queue and single server, then you know what happens to ages. You know, every time step, the ages go up deterministically by 1. We're clearing a packet with probability mu. And when we do that, then the expected decrease in age is 1 over lambda, because that's the expected gap between 2 packets. So the long run, the aging rate should be this. You know, either 0, as in not aging, or 1 minus mu over lambda. You grow up by 1, you decrease in expectation by mu over lambda, and indeed that's a correct number. And that happens in the bigger system also. I guess this is the actual expression. 1 minus, so this is the aging. This is the which this set of packets clear. Consider a subset S. This is the total arrival rate, and this is the total successful service rate. That is the mu's of the servers they managed to send to in expectation. And I guess I should look at this number for every subset, and the worst subset, that is the one that ages the fastest, is indeed the worst, and then ages at this rate. And then I should just recurse the rest of the packets, and that gets all the subsets right. There are some nice structural properties here. Tight subsets or maximum rate subsets are closed under union and intersection. Aging rates are continuous in the probabilities. And then using these kind of things, you can prove relatively easily that Nash equilibrium exists on a classical fixed point theorem. I guess using concentration and other things. Maybe the more interesting part is the price of energy proof, which I also will not spend a lot of time on due to running out of time. But remember, my claim is that the symmetric profile is the worst case. And what we do is, again, is an equilibrium analysis, take a Nash equilibrium and slowly deform it to become this essentially symmetric profile. And then indeed, by making it better and better and better, and that says that the symmetric profile is as bad as it gets. and maybe I
So
will
the
not.
optimum here is each one goes to first queue to the first server, second queue to second server, and so on. That's the optimum, right?
That would be the optimum, yeah.
That's optimum. The Nash is they all compete on all of them, and some of them therefore don't get served on time, and that's where you lose the E over E minus 1 or whatever.
Exactly.
Yeah.
Exactly.
Okay. Good.
So I had a couple of slides for this proof too, which I'm going to maybe mostly skip, but go back
can
to.
you just explain what's the semantics of this, say 2773 division? What does it mean?
I guess maybe best is the example I actually coming up, or
Yeah,
why
even
is
this one over, yeah, this one,
Yeah.
for example.
that one. So what's happening in this example, and it most shows the difficulty of the proof and maybe even some idea of the proof. And I'm going to stop just showing the example. So what's special in this example? If I look at what's happening in this example, there are very many sets that are being served at this maximum rate. So one subset is this. This pair of queues, even if I ignore the rest of them, even if I assume these guys would have somehow priority or the other two wouldn't do anything, they only get served at well enough if lambda is less than this 0.773, because doubly enough, they compete here. Like they're wasting some capacity. When are they wasting capacity? When both of them come to this central server, then one of them gets rejected. And that's a wasted capacity that's happening here. And I have to give just the two of them enough capacity to compensate for this waste. Why are they wasting capacity? Because this triple set, or why is this guy wasting capacity? This triple set is also tight. So whenever thinking of three of them, they waste capacity in two different ways. One is they compete here, one is they compete here. So no matter where this guy goes, somewhere we're wasting capacity. And similarly, the other three, and actually the four of them combined also are tight. So every set has the property that that there's the same limit on how much lambda can grow, just focusing on that subset. Which means that any server, if they chooses to do something different, it only makes life worse for himself. It makes one of these tight sets even more tight.
So the 0.27, 0.73, that holds for every lambda or for the maximal lambda at which the system is stable?
This is the maximum lambda that's stable.
So there is a certain lambda.
But in this particular sending rate, that's the maximum lambda because of these two nodes, because of these three nodes, because of these three nodes, and because of these four nodes. There are very many sets that are simultaneously limiting you to the same lambda. And if any one of you tries to move away from this, then one of these four sets gets worse. Some of them get better, then one of them gets worse, which is why it's tying in as a Nash equilibrium. Like you can't move away, and for different people or different moves, it's a different reason, but none of you can move because if you do something, one of those four sets gets worse.
Is it clear that if you consider coalitional moves, things will just clear up? Say I think of strong equilibrium instead of Nash equilibrium.
That's a nice question. About this particular example, the best lambda can get coordinatedly is 0.75, and what we get here is 0.73, so I'm barely losing anything. And in fact, this is the best Nash here, so there's nothing much you can do, even in a coalitional way. But for example, in the symmetric solution, obviously, yes, you should all just agree that you choose your own server and everyone is perfectly happy. So there might be a nicer theorem here in coalitional Nash than what we can do.
A question, I mean, much of the play here is your rule that oldest is served first. And that means that if you are screwed, then you get priority next time. What if you change that rule? how are the results going to change? I mean, you could even go to the other extreme, you know, that somehow the youngest gets served first. And then clearly, you know, there is going to be one queue that's going to go very quickly because they'll get priority until it ends. And I don't know. I mean, that will change the analysis. Somehow, I feel that that's an important assumption.
Yes, that is an important assumption. And maybe I have a hidden slide that tries to answer that question. So let me try to show my hidden slide. Here it is.
Or even just a random one.
So this actually, I didn't think of Sergio's question, but the example shows that that would be even worse, is exactly Michal's question, the uniform random. Suppose the truth is that one of them gets served and other gets sent back and it's chosen uniformly at random. So here is a bad example for that one. There is a queue that has packets, gets packets all the time in a constant rate. Everything else is 1/n roughly the rate. And there is a really good server that would be his favorite server. And there are many, many problematic servers, but see the way this is set up, if everyone sends to their own server, they all get cleared. You know, no build up any place because there is a factor of C is some sort of constant. That's a slack in the system. There C some constant increase in capacity compared to the arrival rate. Any constant C, in fact, it could even be super constant. This is not the selfish outcome, especially not on Sergio's objective function, on which the goal of these queues is to get the packet served as fast as they can, because you know, these are pretty bad servers, constant over n. So in expectation, you have to wait something like n steps to get served. Luckily, you know, you only get packets every n steps also. So this is not causing a buildup, but it's annoying. For randomized choice, the unique equilibrium is that they all or almost all of them send to the top server. What happens there is because there are n of them, your probability of getting served is 1 in n, which I guess is, or maybe don't go all the way up to, and some subset of them go up here. You can get the service rate better than what these servers give you. But that really sorry, what happened here? That really screws the big queue, is not getting enough service. So the eagerness of the queues that don't have much packets to get their packet served fast kills the ability of the big queue to get served. And what the priority scheme does is gives them advantage because they get so many, they packets tend to be older. And I think your youngest first only makes it worse.
Yeah, of course.
So I guess I didn't want to tell you the proof sketch, and I didn't, just end with the conclusion. So I think there are many interesting games where there is carryover effect. And these packets are the ones that I know how to prove anything about. One that's sort of more classical or more famous or people more think about is auctions with budgets. The carryover effect is the budget. When you successfully bought something, you have less money. When you fail to buy something, you have more money. That's a carryover effect. Or maybe put it more pointedly, if I lose all the time to Sergio, or Sergio eventually won't run out of money. And so maybe that's there's a long-term benefit of some strategy that no regrets not taking into account. I think no regret learning can be too myopic or simplistic. And my question is, can you do something better? And I like asking the question of what's a good learning method for each of the players. There is a NeurIPS 21, so I guess half-a-year-old paper now by Centenac, Persier, and Perchet actually motivated by our paper suggesting that they can offer a cooperative solution in which packets clear optimally. I'm hoping that with some learning algorithm with a bit more foresight in it, like you not just explore, exploit, but stick to the exploration, see the long-term effect before you start trying something else, will be good enough to get this E over E minus 1 band or something possibly even better, but I don't know. And I'm going to stop here and thank you very much for your patience. And I see I ran over time. I apologize.
Thanks, Eva.